from unwanted meters, we have, as we have discussed earlier, 8 meters, and slack bus we have always, and add Gaussian error to mimic metering error, which has 2% Gaussian error, and then finalize. And then this neural network, this finalized data set is ready for our neural network training. So for the neural network training, the data set is used to train 91,503 samples. But for this purpose, we have separated our data set 91,503 samples in two categories. First one is for 91,000 for only training purpose, and 503 samples for the checking of robustness, that how our model is trained perfectly or not. So these 503 samples are not taking part in the neural network training. And 91,000 samples also take part in the division, which is for training, validation, and test for 80%, 10%, and 10% respectively. Best results were obtained with two hidden layers having 18 and 16 neurons respectively on each. But means we have based our model in two hidden layers. First one is for 18 neurons, and the second one on 16 neurons. So this table shows the comparison between actual values and predicted values of our model. So actual values are the values which we are generated from the MATLAB coding. So these are ideal, and the predicted values are the values which take part from our NN based line current estimator model. So from this model, as we see here, we have used 367 sample and 412 sample. As I discussed earlier, I separated our data from 503 samples which are not taking part in neural network training. So from that sample, we have picked random samples 367, and these are the values, actual values and predicted values. So here we can see there is minor differences. So our model is perfectly trained. And the conclusion of our work is a framework has been proposed for distribution network for feeder current prediction based on large data set and generalized data set. Deep neural network line current estimator with best architecture is input 1816, which is a hidden layer, and output has been developed and tested with satisfactory performance at various loading scenarios. Satisfactory means we have generated our data set, we have limitation of our computational sources. So our mean square error has achieved is almost nearly tends to 0. Equal to 0. It means this is satisfactory performance. And the future work of our experiment is we have fixed the topology, and this limit will be considered in our future work. A small distribution network has been tested and will incorporate a large network in our future studies. We have used 15 bus IEEE system. Then we can use any system of distribution network in our future studies, and we can also make a GUI network of this model in our future studies. And these are the references which are taken in the research paper. So thank you.
So thank you very much, Sharjeel. It's a good presentation. There are a few observations related to your presentation and some technical queries which I want to get clarification. Can you open your presentation, please? Yes, it's been very difficult for me to locate from where do I have to ask any question, because you didn't put slide numbers here. So in future, whenever you make presentation, it's important to put slide number. Anyways, one thing which I am still not clear about: did you generate the data sets, or you just collected them from internet?
No, I'm not collecting from internet. In research paper, we have मतलब कि हमारे पास एक ऐसा डाटा था तो सर p की वैल्यू वैल्यू दी हुई थी हमें स्टैंडर्ड लोडिंग कंडीशंस के ऊपर, तो हमने क्या किया, मैटलैब को उसको परसेंटेज तक वेरी किया है और
all the data sets by yourself
यस
only through simulation.
यस
Then how can you know that in the actual situation, which is already reported in the literature, you are going to get the same values for the same design?
because we have used run load flow analysis backward forward sweep method and ये हमारे रिसर्च पेपर से भी यानी कि मैच कर रहा था हमारे जो वैल्यूज थे नाइन करंट, तो उसमें वैल्यूज गिवन थी, पहले हमने उसको रन लोड फ्लो रन किया, उसके बाद देखा कि हमने ईटर पे भी हमने किया इसको काम, तो उसको जो काम आया वो उसके बाद हमने अपने डेटा सेट को बेहतर करने शुरू किया इसके बाद से।
Because generally when people work on on these algorithms, they make a library of their data sets and they collect that from internet or from other libraries or resources.
Yeah.
But you generated your data sets
From MATLAB coding.
Second is in the table where you've been showing the number of data sets. There was a table. I don't know the slide number. I think that was in the middle. That slide was in the middle. और पीछे गई नहीं, आगे नहीं, जहाँ पे कि आपने मेंशन किए थे कि हाउ मेनी नंबर ऑफ डेटा सेट्स आर देयर, few were in order of 10,000s,
Yes, yes.
some were in the range of thousands. So I just want to ask that why their numbers are unequal and why there is such a big difference. Like for example, you are having 257 data sets also, and then why their numbers are unequal?
हमारे पेपर में गिवन था, पेपर में जो एक हमें लाइटली तो नेगेटिव 0.65% की लगी थी, 0 से लेकर 160% ये वाला जो 28,000 हमने 1 by 1 हर बस के ऊपर हमने वेरी करना चाहिए, मतलब हमने अपना जो डाटा सेट बनाया मोर जनरलाइज्ड डाटा सेट बनाया है कि एक बार हमने पी को वेरी किया एक एक करके, P1 को वेरी किया, P2 को वेरी किया, P4 को, उसके अकॉर्डिंगली हर एक डाटा सेट के ऊपर हमने लाइन करेंस को निकाला है, तो इसलिए इसमें ज्यादा है। और जो 257 है वो एक साथ ही P सारे P1 P2 P3 के ऊपर लाइटली चलेगा, हेवी तक वेरी हुआ था, तो इसलिए 257 है।
So what do you think, which one is better, having a large number of data set or a small?
Having a large number of data set.
Then you should have taken a large. 257 is enough. It's not a bad number, but again, there is so much difference in the number of data sets. Okay, in your in this abstract book, you mentioned that you will be extracting parameters and system voltage and line current are mentioned here. But the result which you have shown here, in those results in the table in the last, you have only indicated
line
results for line current. So what about system voltage?
About paper.
Okay, but it's mentioned in the, maybe it's a general statement which you have mentioned in your abstract. Okay, thank you very much. That's all from my side.
Okay. This is a very good presentation. अच्छी effort है आपकी माशाल्लाह। एक दो चीजें मैं भी जानना चाहता हूँ. So my question is regarding the number of layers, hidden layers used. आपने ये कहा कि जो है वो जैसे उनकी हमने कम किया तो रिजल्ट बेटर हुआ. What is the rationale behind? आपने इसको इन्वेस्टिगेट किया है?
मैंने कहा था कि शैलो न्यूरल नेटवर्क अगर होता है तो उसमें एक हिडन लेयर होता है, हमने डीप न्यूरल नेटवर्क पे काम किया है, 2 हिडन लेयर्स हैं और हमने हर न्यूरॉन्स के ऊपर अपने चेक करना है, यानी कि नंबर 1 न्यूरॉन पे चेक किया, नंबर 2 पे किया, नंबर 3 पे किया, ऐसे हमें जो फर्स्ट लेयर पे मिला वो 16 न्यूरॉन पे बेटर रिजल्ट मिला था फर्स्ट लेयर के ऊपर। फिर हम सेकंड लेयर के ऊपर चले गए, फिर सेकंड लेयर के ऊपर वैसे हमने वेरी करना शुरू किया, फर्स्ट न्यूरॉन पे चेक किया, सेकंड पे चेक किया, 1 से लेकर 30 तक चेक किया हमने, तो 18 पर रिजल्ट बेटर आया मीन स्क्वायर एरर को देखते हुए कि मीन स्क्वायर एरर।
आपने नंबर ऑफ न्यूरॉन्स पर लेयर की बात की?
जी, नंबर ऑफ न्यूरॉन्स पर लेयर की बात की।
और दूसरी चीज ये कि जब आप रैंडम नॉइस इंक्लूड करते हैं
जी,
तो आपके रिजल्ट्स जो हैं वो रिप्रोड्यूसिबल नहीं रहते, इसके बारे में क्या कहेंगे?
सर रैंडम नॉइस हमने 2% एरर इसलिए ऐड किया क्योंकि बाकी रिसर्च पेपर के ऊपर देखा था कि मीटरिंग एरर में जो है तो मैक्सिमम 2% एरर्स आ रहे होते हैं, तो हमने इनपुट कंडीशन के ऊपर ही सिर्फ अपना नॉइस ऐड किया है, आउटपुट पे ऐड नहीं किया, क्योंकि इनपुट पे जो हम रीड कर रहे होंगे, क्योंकि अगर हमने इस पे मैटलैब कोडिंग के थ्रू किया तो वो आइडियल वैल्यूज हैं, अगर वो 10.2 पर एक लाइन करंट दे रहा है तो हमारे पास जो मीटर के ऊपर आ रहा होगा 2% एरर के साथ आ रहा होता है मैक्सिमम, तो इसलिए हमने किया था।
Thank you, Sharjil, for your presentation. I now request Mr. Sharik Sheikh from NED University to please come up to present his paper on the estimation of technical losses on transmission systems using neural network prognosis algorithm.
Assalamu alaikum everyone. This is Sharik Sheikh from Department of Electrical Engineering, NED University Karachi. Today my topic of presentation is estimation of technical losses on transmission network using neural network prognosis algorithm. Basically, we all know in watts and megawatts in transmission network, and it is very crucial to estimate those losses so that you can take the corrective measures. So, really, flow studies, we first calculate voltage, and then we reach to this value of the losses on the transmission network, which are active and reactive losses of the network. So the techniques that are usually used are very time consuming, and it also depends on the size of the network on which you are dealing with. So nowadays, as the interest is towards the application of deep neural network or the artificial field, so one of the field is power system, and therefore I area that how can we estimate the transmission system network losses through the using deep neural network technique. So neural network architecture is basically, as shown, has some input layers, some hidden layers, and one input layer, then some hidden layers depending on the network or complexity, and then we have some output layer, which is actually the prediction of the parameter you are going to calculate. Input layer, hidden layer. So how the neural network works, basically, you give a series of input data, and usually we name that as a data set, which comprises of large number of samples. And in power system, you have two options to get the data. Either you have some real-time monitoring systems through which you are getting the data, or you have the simulation software through which you can make models and then find out the operating scenarios of the system, and then you train your network on this data. So here, what is the scenario? Basically, if you see that in the network here, we have different meters located. This is a transmission network. in the last paper, the student showed the distribution network of the system. So here it has a transmission network, and there are some localized central, just like we have in K Electric. SCADA system is located in the main head office building there, and they are collecting data from several locations, and then they are manipulating different things. So what actually happens that all the meters sending different data to the centralized location, and there all the working is carried out to find out different parameters. So when we send data from these meters, so there are inaccuracies either inherent in the meter that it is unable to capture the total actual value or the ideal value, or there are some communication losses also. So in our experiment, we have modeled this network through the coding on MATLAB, and then we have operated the system on various loading scenarios, which are usually possible in transmission network, and then we calculated we trained our network on that data and find out the transmission losses. So in order to make it realistic, we have added Gaussian noise to mimic the real world scenario. Like we have seen in the previous paper also, the author has also added the Gaussian noise to mimic the real world scenario. And here I have presented the conventional technique and AI based technique comparison. Here you can see in Gauss-Seidel or Newton-Raphson, what we do, we first calculate the complex voltage, which is the sole purpose of the load flow study at all the buses in the network. After finding the voltages at each bus, we calculate the line currents in each of the lines. And then we find out the sending end power, receiving end power, and the difference of the power basically gives us the estimate of the power loss at each line. And then we sum it up to find the total loss of the system. So this is an iterative process in the first step, and then there are analytical procedure or classical method to calculate all these parameters. And finally, you get megawatt and megawatt losses. So what I have tried to do, I have tried to bridge this gap by inputting the loading values of the operating system and then directly predicting the losses. So all the computational time that was used in the conventional technique has been bypassed. The only you have to train the network. It will take time, but once trained, it will perform really, really well. So what happens here that we have prepared a data set for neural network training. Then we have tuned some parameters of the deep neural network model to find out the best model. Then we can provide some unseen data to the model to have estimation or predictions of the new operating values. So here you can see that I have generated the data in two scenarios. Usually transmission network do not vary very much from zero condition to 160% of the condition like we have in the distribution network. So there are narrow operating range. So I have manipulated the lightly to heavily load condition. And lightly means you have manipulated or calculated the values or varied the value between 90% and 10% of the network base value. And then in the random values, because this is the more appropriate scenario that we do not know what will be the loading scenario or the loading pattern actually. So the random loading patterns have been generated, and altogether 44,010 samples were generated. So because in some of the practical scenarios, you know that transmission network might behave as a reactive power source under lightly load condition. So therefore, as the title of the paper was that we are predicting the loss, active loss and reactive loss, therefore we have to filter out the data, and we left with 12,383 samples after filtering out those cases in which the transmission line was behaving as a source of a reactive power. That is, negative Q values were provided by the network. Okay, so then we have entered our data into the model or coding through which we have developed a more practical scenario. I have segregated the 14 bus system into 3 cases scenario in which I have added different amount of noise in different meters, because that is more practical. That it is not possible that all the meters have same amount of error at a time. Okay, it might have, because of the aging effect of the instrument and some other issues, there can be, or some distance of the communication, there can be a noise of different level in while achieving the data from different meters. Therefore, I have segregated the data into 3 slots: meter 2, 3, 5, I have added 0.5% error. Then meter 4, 6, 9, 12, I have added 1% error, and meter 10, 11, 13, 14 were added with the 2% of error. So it generated a more practical scenario data that different meters have different amount of inaccuracies in them, and they are sending data to the central command, and then we are predicting the losses. So we have merged that error data and removed the data with Q generation condition, and finally I have obtained the data for the neural network for the training. And before training, we have the data set outlook in this form that you can see that there are some loading values. These are the load values from the active power loads in the network. Then we have reactive power loads in the network, and on the basis of which my model will be predicting some losses. Okay, so these are the loss values, active power loss and reactive power loss in the network at some loading pattern. So as we have here, we have 6 input samples I have shown, for example, so 6 system losses values are there. So for each, now we have a data set prepared, then we provided that data set into the DNN model for training, and trained the model and find out that on 12 input, 22 inputs, because there were 11 load buses, so 11 active values and 11 reactive values were there, on which I have trained, we have trained the data, we have trained the model. And after started tuning from the very scratch, we have varied the neurons and find out that the this architecture with input layer, hidden layer, and output layer was predicting very good. So this was the performance graph of the model which was trained, and it definitely took a large large time for the training purpose. And then we are getting about 99% accuracy in our model, so which was predicting very well. So this was the research that I am presenting, and you can see that the development of data set we have used has a limitation that only normal operating scenarios has been considered, or the normal topology. But in transmission network, usually it doesn't happen. It might happen that there can be a n-1 contingency that can occur. One transmission line fails, but the system has to remain intact, and it has to deliver power to the loads, and the losses will always be there. So that is our future recommendation, that by varying the topology of the network, we will be creating the similar type of data, but also we have to provide some information regarding the topology so that neural network can pick that also. Okay, so that's all from my side. These are the references that I have used for it. Thank you very much. Slide. Presentation from
like to just ask, in this study, have you selected a feeder data or a grid data? Like on what area is this realistic data? And
as I have.
can you give me some time? Thank you. And can you please show what were your impacted results, because those errors were like too small to see. So I would just like to hear that. Thank you very much.
Basically, as far as the generation of the data set is concerned, as I already mentioned, that it was simulated, or basically I have prepared the coding through which I have generated this data set for the different operating scenarios in the transmission network, and definitely after the load flow carried out, the losses were stored. So this is how the data was prepared. It is not a realistic data, but if you find in the literature, basically there is no you can say a benchmark data available on the network regarding the power system, because it can operate in so many ways. Therefore, people are creating data set as per different scenarios, and therefore I have also modeled or created the data considering the likely to heavily loaded condition and the random operating scenario.
Okay, thank you, Sharid. A good presentation, a good research work presentation, and I feel like that this work is also somehow connected with the previous presentation,
Basically,
right?
he is my final year student, and I was his supervisor. And this was the work done by one of the faculty member who is in right now in US
Mhm.
for his PhD persuasion. So these are the two papers that we have submitted in the power system domain regarding application in neural networks.
Okay, so what I understood from the previous presentation and from your presentation, that for for the detection of any kind of parameters, extraction or estimation of losses or whatever, so what you people are doing, that you are generating your own models, you are introducing noises of your own choices or error percentages of your own choices, right?
Basically, they are in the literature. Given in the literature, that this amount of data
And
usually.
then you perform simulations on MATLAB, and it's it is good, but usually there are many algorithms and functions available.
Yeah, there are many
That's okay.
softwares.
Yeah. The main thing is that how you would verify that your results are credible. How will you check?
Load flow studies are giving you the ideal data that should be the losses on the system while you are performing the studies. And AI is just reducing that time and giving you the values nearby those values, which should be the values in the actual scenario.
So have you compared your obtained results with some already published or reported?
Basically,
results?
the situation is that this the scenario basically changes with the sort of the data you are giving input to the network.
Mhm.
Basically, in literature, you just find that an author has varied the data from 80% to 130% in this manner, and he has obtained this data set and then prepared this model. So we don't know that what was the actual values he was using and how he was generating the data set. We just know the IEEE based values,
Mhm.
and then we manipulated the data according to our own wish. That
So there is not any well-established rationale for generating the values?
no.
No. Okay. Thank you very much for the presentation.
अस्सलाम शादिक, गुड प्रेजेंटेशन। अच्छा, मेरा एक सवाल ये है कि हम एआई मॉडल बना रहे हैं न्यूरल नेटवर्क पे, इसकी डेटा जो सेट है उसकी कलेक्शन सोर्स के।
देखिए रेहान, मैंने पहले भी मेंशन किया था कि दो तरीके हो सकते हैं। जस्ट लाइक इफ वी इन फाइनल ईयर प्रोजेक्ट्स आस्क डाटा फ्रॉम के इलेक्ट्रिक के भाई आप हमें रियल टाइम सिनेरियो डाटा दे दें, तो यही वैल्यूज अगर उनके पास 11 लोड बसेस लगी हुई हैं तो वो भी हमें 22 रोज का डाटा ही देंगे, जिसमें पी और क्यू की वेरिएशन होगी और आउटपुट पे ये लॉसेस होगी।
डेटा सोर्स तो है हमारी ट्रांसमिशन लाइंस पे ना
जी,
लेकिन समटाइम्स ऐसा होता है कि कोई नॉन कम्युनिकेटिव चली बाय नहीं,
जी जी,
कोई भी मसला।
हाँ,
तो अब आपका जो मेन इनपुट है वो है डेटा सोर्स,
जी,
जो डेटा सेट है आप, अगर उसमें ही कुछ मसला हुआ,
हाँ,
जैसे मैम ने बोला, तो फिर आप आगे उसको कैसे फिल्टर करते हैं?
ये डाटा सेट लॉस हो जाना तो वो एक अलग बात है, लेकिन जाहिर सी बात है अगर आप अनरियलिस्टिक डाटा पे ट्रेन कराएंगे तो मॉडल को तो ये बात नहीं पता कि आपने जो डाटा दिया है वो वेदर इट एक्चुअली अकर्स इन द पावर सिस्टम और नॉट। तो वो नॉन लिनियरिटी को पिक कर रहा है बेसिकली, वो इस चीज को जस्टिफाई नहीं कर रहा कि आपने डाटा सेट दिया क्या है उसको। तो डीप न्यूरल नेटवर्क मॉडल हो या एआई का कोई भी मॉडल हो, आप उसको जो इनपुट दे रहे हैं वो उसी को सच मान के उसमें जो नॉन लिनियरिटी है उसको पिक करके आपको प्रिडिक्ट करके दे रहा है जल्दी बेसिकली। तो अगर जितना ऑथेंटिक आप डाटा देंगे तो आप उतना ही ज्यादा उसको प्रैक्टिकल वे में जो है वो यूज कर सकते हैं डाटा।
इस चीज का क्या होगा कि डेटा कितना ऑथेंटिक है?
उसके लिए बेहतर ये है कि अगर आपके पास कोई एक्चुअल लोड प्रोफाइल्स हो सिस्टम की, तो उनकी बेसिस पे डाटा बना लिया जाए। तो अगर रियल टाइम डाटा मिल जाए कि भाई लोड प्रोफाइल पूरे साल की क्या चल रही होती है आपके पास, तो उस बेसिस पे अगर हम मॉडल को ट्रेन करें वो ज्यादा बेहतर आपके प्रैक्टिकल अप्रोच जो है वो देगा। लेकिन हमारे पास एक्चुअल लोड प्रोफाइल नहीं थी तो हमने सिस्टम को मुख्तलिफ वे में वेरी करके डाटा सेट प्रिपेयर करा।
थैंक यू।
ठीक है, सो यू कैन से दैट इट इज अ फ्रेमवर्क टू प्रेडिक्ट लॉस एस्टिमेशन इन द नेटवर्क। थैंक यू।
Thank you, sir, for your presentation. I would now like to call Ms. Taskeen Junaid Khan from NED University to present her paper on the voltage collapse prediction using artificial neural network.
voltage. Assalamu alaikum everyone. This is Taskeen Junaid Khan from Electrical Engineering Department, NEDUT, and I'm honored to be here today to present the research on my topic, voltage collapse prediction using artificial neural network, along with my co-authors, Dr. Abdullah Munir, Aisha Ijaz, Atika Asif, and Aisha Uruj. Over the next few minutes, I'll walk you through the findings of my research and the methodology I used to arrive at these findings. So let's dive in by understanding the core problem that I set to address. Voltage collapse is a critical problem in electrical power systems. It refers to a sudden and significant drop in voltage levels, leading to instability and potential failure of the power system. Voltage collapse occurs when the demand for electricity exceeds the system's capacity to supply it. Factors contributing to voltage collapse includes overloading, voltage regulation issues, reactive power imbalance, and faults or contingencies. Voltage collapse can result in blackouts, equipment damage, service disruption, and economic losses. As a result, the objective of guaranteeing a continuous and reliable supply of energy to the consumers is challenged. So, a power system's primary goal is to preserve the system's reliability. Maintaining the system's voltage and frequency within the permissible limits prevents tripping and collapse. If any of them, of both the voltage and frequency, reduces or exceeds those ranges, then the reliability of the system is compromised. In order to avoid the condition of voltage collapse, we need to predict the state of the buses in the power system network. So, in order to predict the state of the buses, we have proposed voltage stability indices. Voltage stability indices have become valuable tools for power system operators in monitoring voltage stability. These indices tell us about the state of buses in a power system network. By keeping a track of these indices, the operators can be made aware of the state of buses and condition of power system before any mishap, and they can take actions to prevent such occurrences. So these indices are predicted using the artificial neural network. An artificial neural network is an excellent approach to predict and solve various complex problems. So in this research, we have proposed two indices that are New Line Stability Index and the Normalized Power Change Index, NPCI. Here are some reasons why NPCI and NLSI are used. Previously, to predict the voltage stability, QV and PV curves methods were used to predict the voltage stability, but they require tedious and difficult computations. Therefore, line stability indices are proposed. NPCI and LSI both are line stability indices. NPCI considers the changes in active power, voltage, and reactive power, providing a comprehensive indicator of system stability, while NLSI focuses on line stability, implementing the inference of line loading on voltage stability. NPCI and NLSI can be derived from real-time measurements, making them suitable for online monitoring and control of voltage stability. Forecasting voltage stability. In NLSI, the bus characterized by the highest index value, that is, if the value of NLSI is close to 1, then that bus is referred as the system's weakest bus, whereas a bus with a lower index value, which indicates that if the value of NLSI is close to 0, then that bus is regarded as the system's stable bus. The NLSI is calculated by combining the line stability index LMN and the fast voltage stability index FPSI using a binary switching function as illustrated in the following equation. The amount of the angular difference between the sending and receiving end voltages determine the value of the switching function. To determine whether the switching function is 1 or 0, the voltage angle values right from the load flow program are compared to the threshold value. Coming to the prediction of NLSI, so here we have employed the artificial neural network to predict both NLSI and NPCI. Let's first talk about NLSI. To predict NLSI, the test system that has been taken here is the IEEE 14 bus system. The calculation of NLSI for both the base and contingency cases has been done. In the base case, the system is running in normal state and the system is stable. While in contingency case, we have created contingency by increasing the load on the buses. The artificial neural network employed here is the multi-layer perceptron neural network. Around 1,000 samples for input data has been taken, and these samples have been trained using the Levenberg-Marquardt training algorithm. And after the successful training of the network, we have tested this network for 20 samples. So our regression plots comes out close to 1, which indicates that our ANN model is trained perfectly for both the base and contingency case. After the successful training of the network, we'll validate and test the model for the prediction of NLSI. Here are the results of NLSI. So these are the predicted values of NLSI using the artificial neural network developed. As you can see, the figure on the left-hand side indicates the base case of the NLSI. In the base case, as you can see here, the values are close to 0, which indicates that the buses of the system are stable and no bus is subject to voltage collapse. While on the right-hand side, we have shown the contingency case of NLSI, in which we have increased the load on the system buses. So upon increasing the load on the system buses, the values are moving towards 1. And some of the values here are exactly 1, which indicates that upon increasing the load on the system buses, the buses are critical to collapse or some buses have collapsed. Okay, now coming to NPCI. NPCI stands for Normalized Power Change Index. It is also a line stability index used for predicting voltage collapse in a power system network. It quantifies the combined effect of changes in active power, reactive power, and voltage on the risk of voltage collapse. The formula for NPCI is shown here as follows. We have both sending NPCI and receiving NPCI. So in case of NPCI, the voltage stability index is predicted for both the buses at the same time, like for the sending end and as well as for the receiving end. While in case of NLSI, only one of the buses is predicted at a time. The NPCI value also ranges from 0 to 1, with values closer to 1 indicating a higher risk of voltage collapse. A higher NPCI value suggests that the combination of significant changes in active power, reactive power, and voltage may lead to voltage instability or collapse. Conversely, values closer to 0 indicate a lower risk of voltage collapse. Now, to predict the NPCI, artificial neural network is employed. But here, artificial neural network is developed using the Python. First, we have to import the required libraries to develop the neural network in Python. Then we'll import the data set that we have created in the Excel file into a pandas data frame. Then we'll split the input and the target variables. Then we'll split the data into training and testing sets. Then we'll scale the input using the standard scaler. After scaling the input, we'll normalize the input data and we'll build and train the neural network. After training and building the neural network, to check if the neural network is successful or not, we'll evaluate the models and we'll check the neural network for our test data. Here are the results after the testing of the neural network. As you can see here in the base case of NPCI, the values of NPCI are closer to 0, which indicates that the buses of the system are stable since it is a base case and we haven't done any contingency. So in this case, NPCI values will be stable and closer to 0. As you can see here, from bus 4 to bus 5, the calculated value of NPCI sending is 0.04 and the predicted value of NPCI sending is also 0.04. While the calculated receiving side value is 0.27 and the predicted receiving side value is also 0.27. So this shows a really negligible difference between the actual values of NPCI and the predicted values of NPCI through the artificial neural network, which indicates that our neural network is developed successfully. Now here is the results of the contingency case of NPCI. As you can see here, the values are now closer to 1, which indicates that we have, upon loading the system is subject to voltage collapse. Some values are between 0.5 to 0.7 and some values are exactly 1. The values that are 0.5 to 0.7 indicates that the buses are critical of the system, and the values that are exactly 1 indicates that the system buses have been collapsed. As you can see here, from bus 14 to 9, the value of calculated sending NPCI is 0.73, and the predicted sending is also 0.73, while the calculated receiving value is 0.817, and the predicted value is also 0.817, which indicates that there is a really minimum difference between the predicted and the calculated values, which also shows that our neural network for the contingency case is also developed successfully. Now, these are the scatter plots that are used to visualize the differences between the actual values and the predicted values of the normalized power change index. The right-hand side shows the receiving end NPCI, and the left-hand side shows the sending end NPCI. Both base and contingency cases are displayed here. The x-axis shows the data points, while the y-axis shows the differences between the actual and predicted values of NPCI. The red dashed line is a zero difference line where the predicted values and the actual values are matched. So as you can see here, the predicted and the actual values are really, they're having a really negligible difference because most of the values lie on this line. So it indicates that our neural network is developed successfully. Evaluating effectiveness with the NPCI. After evaluating both the indices, NPCI and NLSI, we can say that NPCI provides a more accurate prediction of voltage collapse as compared to NLSI because NPCI considers changes in both active power, reactive power, and voltage, while NLSI only considers reactive power and voltage. NPCI reflects the dynamic behavior of the power system by considering the interdependencies between active power, reactive power, and voltage. NPCI is applicable to a wide range of operating conditions, including normal and stress conditions. NPCI can be customized and adapted to a specific power system characteristics and operating conditions. So to conclude, we can say that NPCI is more accurate and dynamic method for voltage collapse prediction as compared to NLSI. ANN is a really powerful tool for voltage collapse prediction due to its ability to learn complex patterns. Real-time monitoring and data acquisition systems enable proactive voltage collapse prediction and preventive measures. In conclusion, our exploration of voltage collapse prediction using artificial neural network demonstrates a promising approach to enhancing power grid stability. As we move forward, collaboration between data scientists, power engineers, and policymakers will be crucial in refining these models and implementing real-world solutions. Let's work together to ensure that our lights stay on, industries keep thriving, and homes remain powered, even in the face of challenging conditions. Thank you so much, everyone, for your attention.
Thank you very much for the excellent presentation. And I have two questions basically. The first one, you have like assigned two indices, NPSI and LSI. And in the conclusion, you say NPCI is better.
Yes, sir.
How you determine that it is better? And in first few slides, you told us like it is from 0 to 1.
Yes, sir.
So what is it's the final value? Like is it treated like a power factor or kind of thing? You just have to mention that. And then what is your benchmark result to like verify that your estimate
accurate for NPCI than NLSI on the same loading.
तो थैंक यू वेरी मच, आपने बड़ा अच्छा काम किया। मैं एक दो चीज़ें जानना चाहता हूँ, वो ये कि आपका जो रिसर्च वर्क है इसमें कोई रेफरेंसेस, कोई ऐसा जो शो करे कि आपकी रिसर्च जो है वो किस जगह पे प्राइमरीली कंट्रीब्यूट कर रही है, थोड़ा इसको एलेबोरेट करेंगे आप प्लीज?
Sorry, sir, can you repeat the question? Sir, application, as far as application is concerned, so I think in power systems, इस चीज की application है. Like, sir, like recently हमने देखा कि blackout की अचानक से condition अगर हो जाती है due to under frequency. So अगर हम ऐसे एक system बना लें कि हम पहले से अपनी buses जो हैं, like हम इस तरह से check कर लें कि कौन सी बस सिस्टम में वीकेस्ट है, कौन सी जो है वो लाइक सर्टेन लोडिंग अगर हो सिस्टम पे, अगर लोड इंक्रीज होता है तो कौन सी बस है जो सस्टेन कर लेगी उस लोड को और कौन सी बस है जो कोलैप्स हो जाएगी. तो अगर हमें पहले से नॉलेज हो कि इतना लोड होगा या इतना होगा तो हमारी कौन सी बस सस्टेन कर पाएगी, कौन सी कोलैप्स हो जाएगी, तो उस हिसाब से हम उस पर्टिकुलर बस के लिए प्रिवेंटिव मेजर्स ले सकते हैं ताकि वोल्टेज कोलैप्स की कंडीशन अवॉइड हो सके, अचानक से ब्लैकआउट की कंडीशन जो है वो ना हो सके.
दूसरा सवाल मेरा ये वैसे मेरा सवाल नहीं था, लेकिन एनी हो, मेरा दूसरा सवाल ये है कि आपने कुछ डेटा शो किया है एक टेबल में, वो उसमें आपने दो पर्टिकुलर रिकॉर्ड जो हैं वो जो करीब तरीन वैल्यूज के हैं सिर्फ वही बताए, कुछ ऐसे रिकॉर्ड जो नहीं बताए जिनमें काफी ज्यादा डिफरेंस शो हो रहा था, इसकी क्या रीजन है?
सर, बिटवीन द एक्चुअल वैल्यूज एंड द प्रेडिक्टेड वैल्यूज, आप
Yes,
उसी टेबल
जहाँ आपने ये क्लेम किया है कि जो आपका नेटवर्क जिसको आप ट्रेन कर
Yes.
रहे हैं वो ट्रेन हो गया है।
यस सर. सर, सक्सेसफुल ट्रेनिंग ऑफ नेटवर्क जो है वो हमने बेसिकली चेक किए यूजिंग द रिग्रेशन प्लॉट्स. हमारे जो रिग्रेशन प्लॉट्स है वर एग्जैक्टली वन विच इंडिकेट्स कि हमारी जो ट्रेनिंग डेटा है और जो हमारा टारगेट वेरिएबल है वो लाई कर रहा है रिग्रेशन लाइन पे, यानी कि उनके दरमियान इतना डिफरेंस नहीं है और हमारी जो प्रेडिक्टेड वैल्यूज हैं वो बिल्कुल एग्जैक्टली मैच कर रही हैं जो हमने ट्रेनिंग के लिए डेटा दिया उससे.
Just one thing I want to get clarification about. You have applied NLSI and NPCI for
Yes.
prediction, right? And you have used IEEE standard 14 bus system.
Yes, yes.
Okay, and 1,000 samples were used. And you compared the results of these two techniques or algorithm techniques, whatever. So has it been done before?
No, ma'am. Comparison hasn't been done before. In fact, NPCI hasn't been implemented before. Like NLSI has been implemented before, but NPCI hasn't been implemented, and the comparison has not been done before.
Because it seems like that for this situation, on comparing these two, you have concluded that NPCI is better.
Yes.
It performs better. So hasn't it been before investigated? You have
No.
investigated it for the first time.
Yes, ma'am. It hasn't been investigated previously.
Thank you very much.
पेपर का टॉपिक आपका बहुत अच्छा था. चूंकि मैंने 2 साल सर्व किया है मैनेजर ऑपरेशंस इंडस्ट्रियल एरिया के इलेक्ट्रिक में, तो ये इश्यूज हमारे पास बहुत फ्रीक्वेंट है. ट्रांसमिशन साइड पर अगर मैं देखूं तो जो आपने यहाँ हाईलाइट किया, जो अंडर फ्रीक्वेंसी पे हमारे पास ट्रिपिंग आती है, जो हमारी एसी ट्रिपिंग हो जाती है, जो लास्ट ईयर काफी फ्रीक्वेंट रही, उसमें दो के वो हमारा मसला नहीं था, लेकिन यहाँ पे यही होता है कि जी वो के इलेक्ट्रिक पे लोग पॉइंटिंग करना शुरू हो जाते हैं. खैर वो तो केटर हो गया है, लेकिन एक इशू जो हमें फेस हो रहा है इंडस्ट्रियल एरिया में वो ये होता है कि एकदम सडन जो वोल्टेज डिप्स आते हैं हमारे पास फ्रीक्वेंसी की वजह से, तो उसमें हमारे पास इंडस्ट्री जो है वो आउटेज में चली जाती है. तो आपके इस मॉडल के थ्रू हम वो प्रेडिक्ट कर सकते हैं?
यस सर, एक्चुअली हम ये प्रेडिक्ट कर सकते हैं कि
मैं क्लैरिफाई करता हूँ कि मेरी एक बस है, मेरी एक बस पे लेट्स से 6 या 7 आउटगोइंग फीडर है उस पे. अब अगर किसी एक फीडर पे कोई इशू आता है कि उसकी वजह से हमारे पास वोल्टेज जर्क्स या वोल्टेज डिप्स आते हैं बस के ऊपर, उसकी वजह से हमारे पास जो इंडस्ट्री जहाँ पे पीएलसी बेस्ड सिस्टम है वहां पे वोल्टेज डिप्स की वजह से आउटेज चली जाती है। तो ये अब बहुत फ्रीक्वेंट हो चुका है इसमें कि इलेक्ट्रिक जो पावर रिलायबिलिटी और फ्लेक्सिबिलिटी पे फोकस करती थी वो अब पावर क्वालिटी पे आ गई है, सिर्फ एक इस इशू की वजह से। तो आपका ये मॉडल उस हवाले से हेल्पफुल रहेगा नहीं रहेगा प्रेडिक्ट करने के लिए?
यस सर, हेल्पफुल रहेगा बिकॉज हम वोल्टेज कोलैप्स ही प्रेडिक्ट कर रहे हैं और वो चीज़ प्रेडिक्ट करने के लिए लाइन स्टेबिलिटी इंडेक्सेस जो हैं वो यूज़ किए जा रहे हैं। सो आई थिंक इट विल बी हेल्पफुल।
थैंक यू।
Thank you, Taskin, for your presentation. I would now like to request Mr. Mazhar Ali from Medan University to come up and present his paper on the demand side management for energy efficient future of Pakistan using low emission analysis platform. Mr. Mazhar Ali. Since Mr. Mazhar Ali is not present here, we will be moving forward to the certificate distribution ceremony. I would like to request Dr. Sadia to please come up and present awards to Dr. Tariq and Engineer Rehan Mirza. Dr. Tariq, please. Sir, yes. I would now like to request Dr. Tariq to please present the shield to Dr. Sadia. I now request the presenters to please come up. Mr. Shazil, please come up on stage for the certificate. I now request Mr. Sharik to please come up for the certificate. I would now like to request Ms. Taskeen to please come up. That's it. Congratulations to all the participants. Ladies and gentlemen, we now enter a brief intermission. You may all proceed to the first floor of the civil department for refreshments. The session will resume in 15 minutes. Thank you.
In case ये